Today we're going to talk about logarithmic functions. Now, logarithmic functions have a lot of properties and a lot of things about them, so we're going to break this up into a couple different videos. So this first video, we'll start with the definition. So a is a fixed positive number, but it can't be equal to 1. That's the same start of the definition of an exponential function. Then we have the logarithmic function of base a, which is written f of x equals log base a of x. That's the inverse function to the exponential function. An inverse function is what undoes a function. So what undoes adding? Subtracting. What undoes multiplication? Division. What undoes squaring something? Taking the square root. So what undoes an exponential function is this logarithmic function. So the way we can write that formally is that if f of x equals a to the x, then f inverse of x equals log base a of x. Now, you can rewrite a logarithm in terms of an exponential function. So what it means, y equals log base a of x, that actually means that a raised to this y power equals x. So it's not a coincidence that we call the base of an exponential function a and that we call the base of the logarithmic function a. That's the same a. When you take the logarithm of something, you're getting the exponent. And what you're taking the logarithm of is the result of taking that base a raised to that exponent. So this is the base, this is the exponent, this is the result. A to the y equals x. So let's get some practice rewriting logarithmic functions as exponential and exponential functions as logarithmic. So what if we had the cube root of 729 equals 9? We want to write this as a logarithm. Well, first of all, to go back and forth between logarithmic functions and exponential functions, we have to have it in exponential form, which means we need to have a base raised to a power. Here we don't, we have a radical. So the first thing we need to do is get rid of that radical. Taking the cube root is raising to the 1/3 power. So now this is the base, this is the exponent, and this is the result. So when we turn that into a logarithm, this is the base of the logarithm. This is what you're taking the logarithm of, and your logarithm, remember, is equal to the exponent, so it'll be equal to the 1/3. So we could rewrite that as log base 729 of 9 equals 1/3. Now let's go the other way. Let's take an exponential expression and write it as a logarithm. Let's take a logarithmic function and write it as an exponential. So if we had log base 6 of 1/36 is equal to -2, the base of the logarithm is going to be the base of the exponential function. What your logarithm is equal to is the exponent, and what you're taking the logarithm of is the result. So we would rewrite that as 6 raised to the -2 power equals 1/36. The nice thing about writing it in exponential form is you can check your answer. We can take 6 and raise it to the -2 power. So remember, raising to a negative exponent, you have to get rid of the negative exponent first, bring it down to the denominator, and then 1/6 squared is in fact 1/36. Now we have two special logarithms that we need to know, and almost every calculator that's scientific only has these two logarithm buttons on them. The first one is called the common logarithm. This is so common, this is the base 10, and it is so common and it's written so much that we actually don't write the base down here. We just write log of x. So if you don't see a base, you have to assume and know that it is 10. The other one is the natural logarithm. This is the logarithm base e. E is that natural base we talked about in 5.1. So f of x equals the natural log, ln for log natural, but we would call it the natural log of x. And you have to know that the base of this logarithm is e. Now, we have some elementary properties of logarithms, and these are very, very important. The first one is that log base anything of 1 is equal to 0. Now, we have those two special logarithms that are written differently, so I'm going to show you how these properties are written in those forms. So for the common log, we would say the log of 1 equals 0. And for the natural log, we'd say the natural log of 1 equals 0. Let's see why. So for example, log base 7 of 1 is equal to 0, following this property right here. But why? Well, how do we write this exponentially? Here's the base, here's the exponent, here's the result. And we have 7 raised to the 0 is equal to 1. Well, think back to our properties of exponents way back in chapter 0. What is anything to the 0 power? It's 1, so that does check out. The next elementary property is that log base anything of itself is equal to 1. So log base a of a is 1. If this base and this number match, they cancel to 1. Now, again, to show you for the two special logarithms, remember this base right here is 10, so the numbers would match, so the log of 10 is equal to 1. And the natural log of e, remember natural log is base e, natural log of e is 1. So, for example, the log of base 6.5 of 6.5 is equal to 1. Well, why? Let's do a check. Log base 6.5 of 6.5 equals 1 means this base raised to this power equals this result. And 6.5 to the 1, anything to the 1 power is itself. The third property says log base a of a to a power is just that power. It's a kind of a build off the last property. If the base of the logarithm and the base of the exponential function match, they cancel each other and you're just left with this exponent. That also comes from the fact that they are inverses of one another. They undo each other. So again, written for the common log, remember you assume that there's a 10 here. The base of the logarithm, the base of the exponential function match, they cancel. Same for the natural log. The natural log is base e. The base of the logarithm, the base of the exponential function match, they cancel. So for example, log base 12 of 12 raised to the 3x minus 1 would be equal to 3x minus 1. The base of the logarithm and the base of the exponential function match, so they would cancel each other. And you can do a check too. Rewrite this in exponential form. This is the base, this is the exponent, this is the result. So you would have log base 12 of 12 to the 3x minus 1 equals this exponent 3x minus 1. Take this base to this exponent, and you get 12 to the 3x minus 1 does equal 12 to the 3x minus 1. So it does work out. So remember, if the base of the logarithm and the base of the exponential function match, they cancel. It goes the other way too. If you have a raised to the log base a of x, the base of the exponential function and the base of the logarithm match, they cancel each other and you're just left with that x. It works for the common log because remember this is base 10. And it works for the natural log because remember this is base e. This comes from the fact that they are inverses of one another and they undo each other. So if we had 5 raised to the log base 5 of 2x minus 1, since the base of the logarithm and the base of the exponential function match, they cancel each other. And again, this comes from the fact that they are inverses of one another, that they undo each other. So let's look at some examples of what a logarithmic function looks like. Let's graph it. So we make a table of values. Now these first two you can pick whatever x values you want. I picked 1 and I picked 2. So if I pick 1 and I plug that into log base 2 of x, log base 2 of 1, that comes from that very first elementary property, it's equal to 0. So then we have the ordered pair 1, 0. Plug in 2 where the numbers would match, the base, log base 2 of 2, again that elementary property says if these two numbers match that they cancel to 1. And we have the ordered pair 2, 1. Now remember what it means. Log base 2 of x gives you an exponent. We'll call it y. So 2 to the y equals x. So the other x values I want to pick need to be nice powers of 2. Like 4. Log base 2 of 4 equals y. That means 2 raised to the y equals 4. 2 to what power is 4? 2, so that's where the ordered pair 4, 2 comes from. Another good value to pick would be 8. Log base 2 of 8 gives you our y value. That means that 2 raised to the y equals 8. 2 to what power is 8? 3. So we get y equals 3. That's the ordered pair 8, 3. Then you could plug in 16, 32, 64, so on and so forth. But that's only going to show you what goes on to the right. We need to look at what goes on to the left. Now, we cannot take the logarithm of 0 or a negative number, but we can do fractions. Log base 2 of 1/2, that's going to give us our y value. 2 to the y equals 1/2. Since that 2 got moved to the denominator, that tells us that our exponent's going to have to be negative. And so 2 to what power is 2? That's 1. So 2 to what power is 1 over 2? That's where the negative 1 comes from. And we'll do one more for good measure, 1/4. Log base 2 of 1/4 gives us our y value. That means 2 to the y is 1/4. Since that 4 is in the denominator, we know y has to be negative. 2 to what power is 4? 2. So 2 to what power is 1 over 4? That's where the negative 2 comes from. So once we plot these ordered pairs and connect them with a smooth curve, you can see this is what a logarithmic function looks like. Now, very similar to exponential functions, if you rotate this 90 degrees, you're going to see an exponential function. It's going to go off forever and ever in one direction, and then it's going to go down, and it's going to have a vertical asymptote. Remember, exponential functions have the horizontal asymptote and no vertical asymptote. Logarithmic functions have a vertical asymptote and no horizontal asymptote. Okay, let's do a couple examples using those elementary properties. So we'll use the elementary properties to evaluate some logarithmic expressions. For example, if we have log of 1 over 1,000, so we want to find what this is equal to, and we're going to do this without a calculator. So remember what the base of the common log is, 10. So log of 1 over 1,000 is going to give us some y value. By definition, what this means is that the base of this logarithm, which is 10, raised to this exponent y, which is what we're looking for, is going to give us 1 over 1,000. That 1,000 is in the denominator, so that tells us the exponent is going to be negative. And 10 to what power gives us 1,000? 3. So we know that y is equal to negative 3. So since 10 to the negative 3 is 1 over 1,000, that tells us the y value we're looking for, that exponent, is negative 3. So we get that the log of 1 over 1,000 is equal to negative 3. Let's do another one. Log base 6 of the 5th root of 36. Well, we don't have any logarithmic properties that help us with radicals. Remember, logarithms and exponential functions are what undo each other, so we need to rewrite the 5th root of 36 as an exponential expression. So we'll raise that to the 1/5 power instead. Now, we had a property that told us what to do if the base of the exponential function and the base of the logarithmic function matched. Unfortunately, this is 6 and this is 36. But we can rewrite 36 as 6 squared. So now we have log base 6 as 6 squared to the 1/5 power. Go back to your properties in earlier sections. Power of a power, you multiply. So that gives us a log base 6 of 6 raised to the 2/5. Now the base of the logarithm and the base of the exponential function match. They cancel each other, and we're left with 2/5. Let's do one more. The natural log of the square root of e cubed. Remember, the base of the natural log is e, but again, we have to get rid of radicals and rewrite them as rational exponents. So the square root we would rewrite as 1/2. So now we have the natural log of e cubed to the 1/2 power. Power of a power, multiply those powers. Now the base of the logarithm and the base of the exponential function match. They cancel, and we're left with 3/2. So that's a good start to logarithmic functions, and we'll continue our lesson on logarithmic functions in the next video.